So let's look at some practice problems using this information. We have the Earth averaging 1.5 times 10 to the 8th kilometers from the Sun. So we would consider that the radius of the Earth's orbits around the Sun. We're going to treat it as a circle, even though it isn't. And we want to find the average daily distance the Earth travels. Well, one way to do it is to find the circumference of the orbit. So we'll take 2 times pi times the radius and divide it by the time. And that will give us the distance traveled per day, since we're looking for average daily distance. 2 times pi times 1.5 times 10 to the 11 meters, and we'll divide it by 365 days, since that's how many days there are in a year. What we get is 2.58 times 10 to the 9th meters, and that's per day. If I remember my relationship of delta x equals theta times r, if I'm looking for the average angular displacement, I'm given the radius. I just found delta x. I can use those two to find the average angular displacement. So what I will do is take 2.58 times 10 to the 9th meters divided by the radius of 1.5 times 10 to the 11th meters, and I get 0.0172 radians. I'm not asked to find it, but my angular velocity is the change in radians over time. My change in radians is 0.0172, and this is for 1 day. 1 day is 3,600 seconds times 24 hours, and what I get is 1.99 times 10 to the negative 7 radians per second. To find the angular acceleration, I just take the change in my angular velocity over time. And so I take 1.99 times 10 to the negative 7 radians per second, divided by the time, which is the number of seconds in 1 day, which is 86,400. And I get 2.3 times 10 to the negative 12 radians per second squared. All right, if we look at number 2, we have compact discs that are actually now a thing of the past. Records were before that, and the most popular records rotated at 33 revolutions per minute. That's what RPM stands for, or 45 RPMs. First thing we are asked to do is convert 33 RPMs to angular speed. So I'm going to take 33 revolutions times the distance for 1 revolution, which is 2 pi radians, and divide it by time, which is 60 seconds, and I get 3.45 radians per second. Letter B asks me to do the same thing for 45 RPMs, so same deal, 45 times 2 pi radians over 60 seconds, and now I get 4.71 radians per second. Letter C, now I have a record that has a diameter of 7 inches, and I want to find the linear or tangential speed at the outer edge of the record. It's a 45 RPM, so I know my angular speed. 7 inches is the radius. That will allow me to find the circumference, but first I have to convert inches to centimeters, or meters more precisely. So 7 times 2.54 divided by 100. So my radius is 0.178 meters. So what we learned is if we take our angular velocity, multiply it by the radius, we will get the linear velocity. My angular velocity for 45 is 4.71 radians per second times 0.178 meters, and I get 0.838 meters per second. All right, my next one, I have a spinning top, 15 revolutions per second, and I have a time that it's spinning, 55 seconds, and it's slowing down during this time. So I have an angular acceleration because my angular velocity is changing. So I'm supposed to figure out the average angular acceleration for the top. So this is a kinematic problem, really. My initial angular velocity is 15 times 2 pi radians. My final angular velocity is 0. My time is 55 seconds, and I am looking for the angular acceleration. So I can solve this with a kinematics equation if I so choose. So I set it up, I solve for angular acceleration. I get 1.71 radians per second squared for my angular acceleration, and it's a negative because it's slowing down, it's decelerating. And let's look at number 4 now. We have a roll of newsprint accelerating from rest. We have an angular acceleration given to us of 15 radians per second squared. We have a time of 180 seconds. Finding out the angle sweep. We're looking for theta this time. Again, another kinematic type of problem. We have an angular acceleration of 15 radians per second squared. We have a time of 180 seconds, and we are looking for theta. We also know, since it says from rest, that our initial angular velocity is 0. So again, a kinematic problem, but this time using, again, our angular equation. So delta theta equals 1/2 times our angular acceleration times squared plus our initial angular velocity times time. What we find for our change in angle, or the angle swept out, is 2.43 times 10 to the 5th radians. 180 seconds is a long time. Now for letter B, if the radius of the roll is 10 centimeters, we want to find out the distance traveled by a point on the outside of the roll. So if we look at the leading edge of the paper, how far will it travel if it's unrolling? Again, we are reminded that delta x, the change in position, is equal to our change in theta times our radius. So we have 2.43 times 10 to the 5th radians. Our radius is 10 centimeters, so that's 0.10 meters. So I have a change in position, or the distance my paper has moved, is quite a bit. 24,300 meters. So 24 kilometers. So it's moving right along. And it's gone quite far.